and see me. Recording has started. Okay. Let me share my screen. Okay. Can anyone just confirm whether you can see my screen? You can see my screen, right?
Yes, sir.
Okay. Okay. We just put this thing away. Put it here. Okay. So we'll first like previous week we started a bit late, so some of you might was like unable to join that class. Okay, I like get some message in the chat that okay somebody has some work to do, so they leave. So we'll just uh, like refresh previous week's like content like for 2 minutes, and then we'll start with today's content. Okay, so yeah, so just so that you know, this is the playlist that I have created for like specifically for this course. So all the videos they will be updated in this playlist itself. Okay, so in any slide, so you can find the slide here, right? This drive link is shared with you. So you can find the slides here for every week and the codes here. Okay, so this is for week 1. Next, I will update today's code as well for week 2, and previous year questions week by week by week. Okay, so it's like whenever you are, for example, this currently you are doing week 3's assignments, so the questions up to week 2 will be available here from the previous run. Okay, uh, okay, so yeah, so you can definitely save this or bookmark this playlist so that you get all the updates or all the, let's say, recording of the videos. Okay, so yeah, so just to introduce myself, because I like last day I was not, I was unable to get a chance to introduce myself. So I'm a research scholar at the Department of Computer Science in IIT Kharagpur, and I works on basically these broad areas. Okay, so artificial intelligence, ubiquitous computing. That means these small sensors, for example, your smartwatch, your Alexa, all those things. So they basically as a group means ubiquitous computing. Okay, so ubiquitous means which is everywhere. Okay, and sensor networks and distributed computing. So these are my key research areas. Okay, so yeah, you can also subscribe to the YouTube channel. Will get notifications when the video will be updated, and some demos are our lab page you can find with these links. Okay, and just so that you know that we are using this Jupyter Notebook IDE for code alongs, just because it is very much easier for us to debug and, let's say, see intermediate outputs. So what you can do, if you have a Python version installed on your machine, you can just do pip install notebook. That will install this IDE, this Jupyter Notebook IDE. Or else, if you don't have a Python installation, it is better to go with this Anaconda manager, which comes bundled with Python as well as a notebook. Okay. So if you don't know or don't have the Python installation currently on your machine, you can just go with this Anaconda manager. Otherwise, if you are, let's say, using Linux, already have a Python installation, you can just go ahead and do pip install notebook. Okay, so that you are ready for whatever we will be doing. Just do it side by side, and whenever you find something not working on your machine, you can just interrupt and ask me. Okay. Now, if you are new to Python, you can go check out this playlist. So this was last session's another NPTEL course, has a lot of good content, slide and code. So if you want to refresh your Python like basics, or you don't know Python, just catching up with this code, so you can just go there and just follow up with the videos. Okay. Okay. So previous day we were doing these things. Okay. So the week 0 is mostly linear algebra, how optimizations are done, right? Those things. So like last day we only see how to implement let's say add, subtract, element wise multiplication, matrix multiplication, transpose and inverse in with NumPy library in Python. So this is numerical Python library. It's a special library. So if you are supposed to do let's say matrix multiplication or inverse in your exam, in your coding section, right? So in that case you will be, I hope you will be given access to this NumPy library, so you don't have to implement it from scratch. Okay. So what we did with this library, after this initial let's say functionalities, we solved a linear system of equations, three linear system of equations, and basic regression theory. We proved that okay, that x transpose x inverse x transpose y, that equation works. Okay. So just for a note, so at that time when I was live, I was confused a bit about the output, but later on I have given, I guess, appropriate. Wait, let me just show you appropriate proof of how it is done. Okay, so you can go to last week's slides. uh, yeah, this one, right? So what we did, what we were doing wrong, we were not appending this beta 0 bias component 1 to the x, right? That's why our whole like shape and all everything was mismanaged. So after you just put a one column at the x and just do the like multiplication of those x transpose x inverse x transpose y, you will get beta 0 and beta 1 like this, these two matrices, like these two values in W matrix. Okay. So that's how you solve like basic linear regression theory that were taught in the class. Now, so today what we will do, so the previous week everything was about like how to use this numerical Python library to basically optimize stuff or do basic operations with matrices. Okay. So today we'll move a bit with theory. Okay. So we'll see what are these general jargons in machine learning community, that is supervised, unsupervised reinforcement. What is the concept of bias and variance in both cases? For example, what is the concept of bias in regression and what is the concept of bias in, let's say, classification, right? Because in both the scenarios, they don't mean the same thing. So conceptually they mean the same thing, but pictorially or visually they don't mean the same thing in classification and regression tasks. Okay, so we'll see what they exactly mean, and we'll see what linear regression is, logistic regression, and their generalized form. So when you have multiple values to regress or multiple values to classify. Okay, so just for a like mm, a kind of hint, this linear regression basically means when you are chasing a single value, same for logistic regression as well. When you are trying to classify between two uh, like different categories, okay? But they will generalize to when you are, let's say, chasing multiple values or chasing multiple or trying to classify multiple categories, okay? So we'll kind of cover this portion today. And for the next week, we'll leave this PCA LDA topic along with whatever there will be in week 3. Okay. So let's just continue. So any questions till now? Anybody? Let me just connect my.
Sir, can you share that drive link to our WhatsApp only, sir?
It's there. It's there. See that week one's resources are pinned, right? So if you go there, there will be this
Yeah.
drive link. Resources. This drive link will be there. Just let me know if you don't find it, then I will share again.
Sir, I've not added to WhatsApp.
Sir, could you share
Huh?
WhatsApp group link here, sir?
Yeah, just anyone, can you please like find while I am connecting my graphics pad, can anyone just share WhatsApp groups like link here in the chat? Okay, graphics pad disconnected. Wait, let me just take this call, okay? Okay. I hope somebody has shared the chat.
Sir,
Okay,
not
let me share. Let me share it. Okay, you should have get the check chat. It will be there. Okay, so let's just go to the content. Okay. Okay. Now, see. So now, hey,
Excuse me, sir.
just unmute yourself. Yeah, go ahead.
Sir, could you define what is a label?
So just wait a bit. We'll explain everything. Okay. So label, we'll discuss that
Okay, sir.
later. Okay. Just unmute yourself, guys. Whoever is creating this noise, just unmute. So we'll see. Just let's say this term machine learning, right? ML. So this term called ML, right? So it has actually three type of like let's say algorithms in it, or not exactly ML. You can group the whole AI like whatever current AI algorithms are there, we can classify them into the supervised. My pen is not working properly, but okay. Supervised, then unsupervised, and then reinforcement, right? So what they exactly mean? Uh, so supervised is when you have, wait, let me, quiz people, new participant.
Sir, it's better to remove people who can't mute themselves and keep disturbing continuously in the class. This is not done.
That's fine. So we'll just, I guess he was not attentive enough. So we'll see. Okay. Uh, okay. So these three types are there: supervised, unsupervised, and reinforcement. Now, what we can think of in terms of how this machine learning set is actually there. So the entire set, let's say it is AI. Okay. Now, machine learning and deep learning and reinforcement learning, actually, these three are main components within current like or modern AI. Okay. So let's say machine learning, a set is there, a deep learning set is there, and what is the difference? That so there is no overlap between machine learning and deep learning. Okay. But there is a overlap between machine learning, deep learning, and reinforcement learning. Okay. So reinforcement learning should sometimes look like this. Okay, so there are machine learning approaches which also which are also used in reinforcement learning, let's say applications, and there are always deep learning applications in reinforcement learning, right? So I guess you have heard this uh, uh, deep Q learning stuff, right? In 2014's paper, so they beat superhuman level performance in, let's say, this breakout game that you are supposed to move a board at the bottom and the ball will jump from that board and you are trying to break tiles at the top of the ceiling. Okay, so those things they come under deep reinforcement, and similarly there are algorithms which take machine learning algorithms and apply it in reinforcement learning domain. So so what is machine learning in general? So machine learning means, let's say I have some data X, okay, and I want a target label. Okay, target label means what I want to predict. So label means so when you have ground truth for example, I want to predict what is the age of a person based on his or her, let's say, foot length, okay, or based on his or her weight. Okay, so let's consider two three features. Let's say foot length, weight, height, something like this, and we will try to understand what is the age of that person. Okay, so what is label? Label is actually when you go and collect some data corresponds to these parameters. So for example, you go and ask let's say a person, what are these parameters for him or her? Let's say her foot length, weight and height, and then ask her age. So this whole pair, right? These are called features. So together these are called features, and whatever data you get from her, let's say whatever is her age, that is called a label. So let's say the her age is 25, so that is considered as the label. Okay, so okay, label.
So, excuse me, sir.
Yeah, go ahead.
So, would you say that the most basic information about any data can be considered a label?
No, see, label always have a intention. Okay, so any information cannot be labeled, right? So so a label is based on your intention. So let's say I am trying to understand what is someone's age based on his weight, height, all those parameters, all those information, right? So my intention is to find out age. Okay, so that in based on that intention, age is the label for me. The data that I, let's say, go and collect from other people. Let's say I go to my department, I ask 10 people about this parameter, this information, and accordingly his or her age, right? So that age, just that 10 ages, 10 age values that I will get, those are considered my labels. And whatever, let's say, other information I get from the person, for example, so in this case, I consider foot length, height, and weight. Those values will be considered as features. Okay. So the entire features and label. So in general terminology, we call it as X and Y, right? Because why we call it as X and Y? Because X, this feature and label has a kind of dependent relationship. So we already know that this X is a independent variable, Y is a dependent, right? So Y is equal to something of X, right? Some function of X. So because
Excuse,
yeah, go ahead.
can we say that label is the output of the feature provided?
Label is the output of a function that takes feature as input.
Yes, the feature is.
Exactly. So that's why this Y has a dependency on X, right? So that's why we kind of name them as X and Y, because yeah, let's say my height and let's say my weight and age has a strong linear relationship, right? So if I know weight, then I can directly come to a conclusion of age, right? So that's why yeah, this and the entire X and Y pairs, right? This is called data. Like let's say data set, what we as data set. Data is anything uh, like organized information is called data, right? But data set, by data set in machine learning literature, what we mean this XY pairs. Okay, so X can be a, let's say, array. It can be one value also, and Y can be one value as well as an array. Okay, so based on your intention, your label would change. And by label, what we mean actual, like real world examples are known as labels. So when you are, let's say, uh, like predicting something, okay, in that case, you don't know the label, you are trying to estimate the label. So for example, just to clarify what is what is, let's say, prediction and label difference. Let's say I have data up till, let's say, equal to 60 kg, right? Data till this point only. So I have the graph only in this domain, right? Now, if I want to predict for weight equal to 70, in that case, I don't have a label for it. I don't have a label. For example, in this graph, if I just extrapolate, it would be somewhere like this, right? Okay. So this is a prediction. Okay. So what is label? When I have ground data or I have collected data from let's say people or person or any let's say physical phenomenon. In that case, that Y variable is called label. When I predicting from those features, that is called prediction. Okay, and the whole theory behind machine learning is my prediction should be close to the actual label. Okay, so what is my goal with machine learning? Is my prediction where I don't know the label should be close to the label if I go and collect it. Okay. So for example, if my weight prediction is, let's say from weight equal to 70, if my age prediction is, let's uh, say 45, right? And I go and collect some data and get it, let's say 46, then it is like, that's what we want. We want our prediction to be as close as possible to the label. But let's say if I go and get actual value to be, let's say 65, right? In that case, my model or my machine learning function, this F, is not good. Okay. So our goal is to make the predictions when I only have X, I don't have Y, Okay. In that case, I want to make my predictions close to the Y without knowing it. And how we test it, how we test machine learning algorithms, we basically keep, let's say I have collected a lot of data means this X and Y pairs. Okay. I let's say I keep some part of the data separate from what I have shown to the model. And later on, when the model is trained or when the machine learning algorithm, let's say, converges or concluded, in that case, I will show the model that unseen data, that hidden away data, and ask the model to now predict on this X, and we'll cross validate with the corresponding Y's we have. Okay, this is how you test models. So basically the testing principle is in machine learning, in let's say machine learning, deep learning, both like these two genres. Okay, so you have, let's say, a big set of X. This is, let's say, the big set of X, and another you have a big set of Y. This is your data that you go and collect it from persons. And now what you do, you, let's say, split the data randomly, or let's say sequentially, keep this hidden away from the model. After the model is trained on this part, you go ahead and ask the model to predict on the hidden part, and like check whether the predictions termed as y cap, y hat. Okay, so predictions are always let's say represented as y hat, and these are true, right? Y. Now what you try to do, we try to make y cap as close to y. So a mathematical way of representing this would be the error. Error is what? Error can be represented as the like difference between them, right? And then you take a modulus. This is the error function. This should be as low as possible. This should be tends to 0. So that means, so if I just expand it, what does it mean exactly? So if it is 0, let's say if I have the optimal case, y cap minus y modulus is equal to 0. In that case, what does it mean? Y cap is equal to y, right? So my predictions are actually true labels. So even if I don't go and collect this y, right? If I only have this X information with me, I can predict this. I don't have to go and collect. Now, why this is useful? So some of you can ask that why it is useful. If I am going to collect X, I can anyway collect Y. Let's say for my this age example, right? So if I go and collect this foot length, height, weight from, let's say, 100 people, why not ask another question and ask the age also, right? So the point is, I can go and ask this data to 100 people, fine, that is okay. But that 100 people, with that 100 people data, I can predict the age of any person in that community. Okay, so why I'm mentioning community? Because let's say this relationship between let's say foot length, weight, and height to age can be different between different communities. For example, within India, Indians can have a different relation than, let's say, Europeans or Americans. Okay, so our observation, this data, 100 people's data, is only from a community or a sample from the population. Okay, not the actual distribution. So I can go with this 100 people data and confidently predict other people's age based on only X. I don't have to, and let's say like most of the time these X variables are, let's say, known to us, already known to us. Okay, so one example could be this weather prediction, whether there will be rain or not, right? So in that case, whether there will be rain or not, this is very hard to guess, right, beforehand. So we don't have this data with us all the time. So what we can do, we can, let's say, observe the weather patterns for a longer period of time. Let's say in India's like where I belong, let's say near Kharagpur, I can let's say observe the weather for let's say 100 days. Okay, and try based on that, I can try predict what will be tomorrow's weather, whether there will be rainy or not. Okay, so that's why knowing this relation between X and Y is important. We cannot go ahead and always ask this Y. Okay, because sometimes this Y is also like very hard to collect, whereas this X is not that much hard to collect. So I can have this meteorological wind speed, wind direction, all of this data from the nearest weather station, right? But the nearest weather station cannot tell me that whether there will be rain tomorrow or not. So that weather station has to use some model, or they have to wait till tomorrow until they can confirm whether there will be rain or not, right? So this Y variable is always hard to collect. Okay, so that's why we were trying to like with machine learning, artificial intelligence, this whole genre of algorithms, what we are trying to do, we are trying to define a set of X, okay, good set of X. So any feature or any information about a phenomenon is not good for predicting something, okay, predicting your intentions. So a good set of features or X should be selected first. So this feature selection is itself a huge topic. Which features I should select? So for toy problem, I select foot length, weight, and height. But that can happen that these three features cannot predict age. Okay, we have to know, let's say, his BMI and every other thing. So BMI is can be compared by height and weight and age. But anyway, so we can maybe we cannot predict age from these three data. Okay, we need more X, more like other values of X also. So selecting a good set of X is important, and then based on that, I will collect a sample of Y. Okay, based on that, I will build a model with whatever algorithm, ML, DL, or like in general AI algorithm, and use that model whenever, let's say, I want to like know whether there will be, let's say, rain today or tomorrow. So I can just go and crawl today's data from the like let's say CPCB server. CPCB is this control pollution CPCB, so control like central pollution something board that deploys basically weather station in multiple cities. So we can get there and call the data from their site, plug it in our model, predict what will happen tomorrow. We don't have to wait till tomorrow. So that's the entire goal of this machine learning, all this algorithms. Okay. Now,
Sir,
yeah, go ahead.
sir, can you once again tell what is Y cap, sir?
Y cap is when you only have the X information and you don't know what will like what is the, let's say you are trying to predict whether there will be rain tomorrow, right? So in that case, that Y cap is you are predicting, okay, there will be rain tomorrow or no, there will be no rain tomorrow. That is Y cap. Okay, but what is Y? Y is when you wait till tomorrow and confirm that, okay, today it rained or it didn't rain. Okay, so Y is basically true. Okay, true. You wait, and this Y cap is basically you predict. Got it?
Yes, sir, thank you.
Okay. So now this whole thing, whatever you have understood, right? So this is known as supervised learning. So this entire paradigm on when you have a X data and a corresponding motive or Y, right? So what it does actually, it helps the model to learn a relationship between Y and X, right? Right, and why it, like how it is done, we are basically supervising the model. So currently, like, kind of assume that model is a black box. Okay, so it's kind of a black box thing, we don't know whatever is there inside. Okay, so what we do to it, we basically put X and Y pairs to it, and it learns some relationship F, okay, between X and Y, so that even if I only give F, even if I only give X, it predicts something. It outputs some Y, which by principle should be close to the true value, true Y. Okay, so this entire notion is known as supervised learning. So when you are supervising a model, that okay, uh, do this when you see this, do that when you see that. This is a supervision, right? So output 1 you when you see A, output 3 when you see B, right? So if X and Y, X are characters, right? I can train a model to do something like this. Output A as a from, like, let's say this is the X column and this is the Y column. So whenever the model sees A, is try to predict 1. Whenever the model sees B, it tries to predict let's say 2. Okay.
Hello.
Yeah, go ahead.
He'll
Hello.
come by 7. That is what he said. He said he's going to come by 7.
Is somebody is asking a question, or is it? Okay, anyway. So I can train a
Sir,
model. Yeah, go ahead.
so what we call as a label completely depends on what we are trying to predict, right?
Exactly. Your intentions are actually defining what is a label, right? So whatever you are trying to predict, whatever your
Very well said.
intention to predict
Got
is,
it.
that true data is called label. So when you have pairs of real world examples, okay. Okay. So now I
Okay,
can,
yes, sir.
okay, good. So so in this case, let's say I want to do something like this, right? So I want to build a model that gives A, C, D, E. In these cases, it outputs 1, and B, B, F, G. In that cases, it outputs 0 or 2, let's say. So I can give these examples. So in my case, so in this case, this 1 and 2 are the label, right? And these are the X. So this is a supervision, right? That I am giving the model. Okay, whenever you see A, predict 1, or whenever you see it belongs to 1, right? Whenever you see F, predict 2, like close to 2, right? So this type of supervision is needed for general machine learning models. So which is called supervised, like supervised learning. So yeah, so in this case, the machine learning part you got, that what is machine learning in general? Whenever you are trying to learn relationship between let's say two parameters, X and Y, where Y is has some dependency of X. Okay, it should not be like Y doesn't have any dependency of X. You are trying to predict a complete separate thing, right? So from my age, I cannot predict tomorrow's weather, right? Or from anybody's age, I
Okay.
cannot predict tomorrow's weather. Yeah, go ahead.
So can you please repeat the supervised learning definition once again?
I'm actually unable to hear you clearly. Can you speak loudly? Hello?
Repeat that supervised learning definition once again.
So supervised learning means when you are supervising something. So supervision means what? You are told what to do, right? So the model is told that, okay, whenever you see A, it corresponds to 1. Or whenever you see, let's not go into this type of technical thing. Let's go for a simpler example, right? Let's say whenever let's say a child eats mud, right? You go and ask him to not do that, right? So that's a supervision. Okay.
So it
So
means we
so
are training a anything what like if we are giving a, it should predict as one. If you are giving C, D, it should predict that particular number.
yeah,
Okay,
exactly.
sir.
So
Thank
you
you.
are basically doing you are basically doing a task of supervisor. So you are telling what to do. Okay.
Okay, sir.
Now, what is unsupervised then? So now there comes an interesting question, right? Okay. So supervision we can relate to, right? Because we also supervise our juniors, right? Let's say my brother or my, let's say, junior lab mate, I can supervise him that, okay, write or like do the experiment like this, or write the paper like this, right? So we can supervise people, so we can relate to this supervised notion of learning. That, okay, I'm giving what to do in which case, right? And the model basically learned that relationship, a kind of abstract relationship between what I'm telling the model to do. So just similar to what our juniors does, right? So for example, if I ask a student of mine to not use bold fonts in their presentations, next time they will not use bold fonts, right? So that's what that person learned from my supervision. So okay, it's very easy for us to understand supervised learning. Now what is unsupervised learning? So in unsupervision, so you are not supervising supervising directly. What the model actually learns, it learns relationship between X to X. Okay. So this is a bit complicated to understand, because so we can put it like this, that so some of you, so for example me, right? I don't like food that that becomes jellies after I cook them. Okay, for example, this um, let's say this cucumber, right? If I boil cucumber, or let's say if I boil gout, right? So these vegetables I don't like. So what I have done, from my preferences, I have grouped vegetables. What I like, I don't like. Right? For example, I don't like whatever, let's say, becomes jellies after I cook them. Okay. And I like whatever vegetables which have some texture. Right? For example, let's say I like so for example, jellies become bhindi also comes in bhindi, right? Or lady's finger, or another name is there, something out. So bhindi I don't like because it becomes kind of jellies after I cook it, right? So, and similarly ground, or let's say cucumber, right? See, but in case other vegetables, for example, this carrot or any other similar vegetables, I like them. So what I have done actually, based on my like preferences, I have grouped some. So what is X here? Can anybody like tell what is X in this case, in this example, in my food preferences? Okay, what is the X I am looking into?
So similarities like whether it's jelly or
No,
not.
jelly or not is based on what I am grouping things. That is my preference, right?
Group all these vegetables grouping.
Yeah. So what is the eggs I'm looking into? So it's not like I just see them and I didn't eat them in like ever, right? It's like I actually have eaten them and then I don't like them, right? So what is the eggs? Eggs is basically my like whatever taste I am feeling in my tongue. Okay. So let's say taste can have multiple. So my tongue have all those neurons in my so my tongue has all those neurons, right? So it is picking up the taste. Based on that, it is signaling my brain. So all the now like neural signals, whatever is coming from my tongue, that is working as a X, right? X. And based on that, what I am doing, what I am basically grouping similar kind of vegetables. So this bhindi or
So
this
isn't that
cucumber,
what
this
I told, sir? Isn't it same as what I told, whether it's jelly like or not?
no, it's like nobody has. So that's see, that jelly is the conclusion I am having, right? So nobody has told me that okay, it is jelly, you should not eat it, right? So it's like it's the conclusion that I am having after eating them. So basically what I did in my brain is that I have eaten the vegetable, I have grouped these similar type of tasting vegetables. So for example, this whatever becomes jellies after I cook them, right? I have kind of given them a common space in my brain that okay, whichever vegetable tastes like this, I will not eat it, right? And what is the label I have given? Because they taste like jelly. That because that thing I get from this relationship from X, right? So what I did in my brain actually is, let's say, a subset of X, let's say jelly, right? They all belongs to a same space, whereas let's say a subset of X that is from texture, they all belong to a different space. And what I have understood from this relation, okay, all this food they taste like jelly, and all this food they taste good. So this label actually I have given. Nobody has supervised me, right?
Yes,
Got the
sir.
point? Got the point that
Yes, sir.
okay,
Got it.
nobody has supervised me that okay, this all vegetables are good and these all vegetables are bad. Good, bad, that is a supervision, right? But from eating those vegetables, what I have grouped, like what I have done basically, I have grouped those vegetables into, let's say, two groups, right? Two sets. That one thing I don't like, one thing I don't like this. So in my brain, this jelly means bad, and this texture means good, right? So this good, bad, if somebody had, let's say, told me earlier, that's a supervision. But by eating them, if I have understood that okay, this jelly, there are vegetables which taste like jelly, there are vegetables which have some texture, and so this relation is known as unsupervised learning by trying things out. So unsupervised learning means you have a set of eggs, for example, this set of vegetables, you go and eat them, group them into two different groups. One can be your like based on which whatever you are liking or whatever you are not liking, right? Whatever you hate eating, right? So this grouping you are doing by your own. There is no supervision as such, right?
Both
Nobody is telling you
the
that. Yeah, go ahead. Go
both
ahead.
liking and unliking vegetables both comes under the X category, right, sir?
Yeah, exactly. The whole thing, the whole set is X. So what I am doing, I am differentiating this set into two different sets. Let's say X jelly and X tea. And based on my preference, I am saying I don't like this. This is bad. I like this. This is good. So this is my
And
preference. But this category,
yes.
this kind of uh, grouping, right? This grouping is called unsupervised learning.
Sir,
Okay, sir.
Okay.
so if
Okay.
we
Now,
take this as a whole set X, sir, so then wouldn't X be the all the vegetables that are there, not the neural system you
no,
told,
no,
sir?
no, 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 no. So vegetables, vegetables means what? I am tasting it by my tongue, right? So the X is whatever I am feeding in my tongue. So what I am doing, I am actually clubbing my. So there are two associations here. One is vegetable to tongue, tongue to liking, right? So vegetable to tongue, this is a one-to-one relation, right? So I can eat a vegetable, I will have a particular sensation in my tongue, and based on that sensation, I can group those vegetables. So vegetables and this, so vegetables are basically yes, like set elements you can say, and whatever you feel after eating them, right? That is corresponding to X because that's what you observe, right? While you are, so you are not seeing the vegetable and then seeing also, right? So the vegetable is not the input. Whatever you are seeing, right? Your visual field is actually input. Okay. So you are, so it's not like you are not tasting anything, you are not seeing anything, you are just blindly, let's say, picking up, okay, this is good, this is bad. You are not doing that, right? Even if you are doing that, you are taking the input from your like skin, right? Your touch sensors input. So from some input, like not exactly the vegetable, you are feeling the vegetable by some means, let's say seeing it, eating it, or touching it, and then based on it, you are grouping things. That okay, this type of taste or this type of texture I like, this type of texture I don't like, right? So up to here, just interrupt me whenever you find it confusing. Okay? So up to here, this is unsupervised. Sorry, unsupervised. So I have actually not used the pen for a while, so the practice has degraded. Okay, so up to here it is unsupervised. Now this, it is bad and good. This association is called reinforcement. Why it is called reinforcement? Because there is a reward component associated with it. So let me just draw a simple diagram what reinforcement means. Let's say there is a world, okay, and there is a agent, and hey, you can just unmute and ask. Don't have to raise your hand. There is a agent, right? So agent means, let's, as for now, let's assume us, right? We are agents. Okay. Now world is what? World is eating vegetables. So world can be, so from the task you are doing, based on that, your world can be, let's say kind of strapped down to what its core components are. For example, this task, this whether a vegetable is good or bad, right? In that case, my world is whatever like vegetables I'm eating. That's my world. Okay. So pick pick a vegetable, then do a eat operation. Based on that, PK vegetable means the C and PK vegetable. Okay, eat it. Let's say good or bad, right? And then you just go and pick another. Okay. So this is the kind of reinforcement cycle you have. And another thing that comes with taking the action at this lower half is a reward. Okay, reward. So what the reward is, whether I like it, whether I dislike it. So supervision is jelly and texture up to here. There is no liking, disliking till now, right? We are just grouped thing. We have just grouped it into jelly and texture. Now this association of jelly being bad and textured being good, how this is happening? Because when I eat this jelly type of vegetable, I feel bad, right? So that means we can represent it as -1 reward. And when I eat, let's say textured vegetables, I feel happy. Okay, so dopamine +1. So now this association that jelly being bad and texture being good, this is called reinforcement. So what is the basic meaning of reinforcement? What I like, I will do it more. What I don't like, I will not do it. Okay, reinforcement means, so by crude meaning, reinforcement means whenever you resupply or let's say you promote a behavior more, you demote a behavior further. Okay, so when which behaviors are rewarding, you promote it. Which behaviors are not rewarding, okay, or penalizing, you just demote it. That's the whole idea of reinforcement. Okay, so this association of jelly being bad and textured being good, this is reinforcement. So I will eat these textured vegetables more than the vegetables which are kind of jellies after cooking. You get it? The whole three type of learning tasks: supervised, unsupervised, and reinforcement.
Sir, can you repeat this? Reinforcements,
Yeah,
both supervised and unsupervised. It's
you got it, right? So reinforcement a bit confusing at this point. Okay, so it is like I will
excuse,
let's say a child, right?
Excuse me.
What? Yeah, go ahead.
Yes, sir. Please continue with one more example and explain unsupervised and reinforcement, sir, so that it will be much more clearer.
Okay, okay. So unsupervised, it is clear, right? At this point that, okay, people kind of group stuffs in their brain based on their kind of features or what they are observing after eating or sensing that thing, right? Let's say, um, uh, let's say you are talking to a group of people. Now what you do, you kind of like group these people based on your comfort, right? So you group some people that, okay, these people I am comfortable to talk with. So these are let's say like where I am comfortable with, and the people I am not comfortable with, right? So this grouping is called unsupervised. So you just go talk to them. So what is X? Your experience of interacting with them. Okay. So based on your interaction, what you are doing, you are grouping people. Okay, these people are good to interact, or I am comfortable interacting with them. These people I'm not comfortable interacting with them. Okay. Now what is reinforcement? The people who are you comfortable interacting with, by talking to them, you feel a sense of happiness, right? So because and the people who are not, you are not comfortable to talk with, you feel a you feel a sense of kind of fear or something negative, right? Right. So what is your next? So let's say you are let's say there is a mandatory thing from your department to talk to all the people for the first day. Next day there is no mandate, right? So for the first day you go talk to everyone, you group those people in your head up, and because you are kind of going and interacting with them, you are getting this reward. So that grouping part is unsupervised. You are getting the reward after talking to them. Next day, because there is no mandate, you'll only talk to those people whom you like, whom you, let's say, like talking to, right? You will not go and talk to someone who, let's say, you feel fear, or let's say whom let's say you feel some kind of insecurity, right? So that association, that grouping is fine. Up to grouping, it is unsupervised. Now, based on the reward or based on the happiness or fear or any other these kind of reward I get, based on that, if I am, let's say, enforcing a behavior or let's say reducing a behavior, so what is the behavior change in your case? So earlier I was talking to everyone. Okay. The next day I am talking to only few, let's say 2 or 3 people whom I like. So my probability of talking to other peoples have been reduced, and my probability of talking to if 3 or 2 people whom I like during the interactions, that get increased, right? Right. So what is happening? Let's say action 1 and action 2. Earlier, your action probability was uniform. So you are taking action based on 50-50. You will go talk to a person A and talk to a person B with the same probability. Next day, after you interact with them, get their views, get to know them. The next day, talking to person A1 becomes higher, let's say 0.9. Okay, and talking to person A2 becomes lower, 0.1. So you are basically enforcing a action A1 and reducing a probability of action A2 based on what you observe or what you get as reward, whether you feel happy or whether you feel sad or fear or some kind of insecurity, right? So based on this entire, when there comes a reward, an association based on it, and your behavior gets changed due to that, this part is called reinforcement. Okay. Now the interaction, so for supervised, unsupervised, there is no interaction, right? You have pairs or you have X data, you try to group them. Okay. So whenever there is this notion of reward comes, then in that case, this belongs to reinforcement. Okay. So in the next day or in the next iteration, you are supposed to take some actions lesser, you are supposed to take some actions with higher probability. Okay. So just to let's say go back to my previous example. So this jelly and texture, this was my understanding after eating the food. So this is my grouping, and based on eating them, based on my my perception, I didn't like jelly type food. Some other person can like that. So that's the beauty of reinforcement. So in different environment, different agents can take different type of rewards. So somebody can like jelly type food, right? So in that case, the reward function alters +1, and then let's say he or she might not like textured fruits or vegetables, right? So in that case, the reward changes, flips, right? But based on my preferences, the reward I took is I don't like jelly, I like textured. So my associations become good and bad. So I will eat textured food more, jelly food less. Okay, but the other person, let's say this is
Sir,
agent
can you give
A1.
some recommend examples of reinforcement machine learning?
Like what type of examples you are looking?
Like which can be used in daily life kind of examples.
Okay, so daily life kind of example, let's say you go and eat chocolate, right? And then you get scolded from your mom or dad, right? So you will not go and eat chocolate tomorrow, right? So that's the reinforcement you are doing in your brain. Okay, I get negative reward after eating chocolate, so I will not go and eat chocolate tomorrow. It can happen that you eat chocolate tomorrow again, you get a bigger scold next day, and then third day you reduce the probability and don't go and eat chocolate. Okay.
Yes, sir. Thank you, sir.
Okay. Okay. Thank you. So this is the entire reinforcement, supervised and unsupervised machine learning. Now, so machine learning. So what I used to refer to machine learning, deep learning, like interchangeably. Okay. So machine learning means there is some black box. Okay, which is called a model. You are supposed to give this X and Y pairs. If it is a supervised learning scenario, if you are supposed to give only X, if you are like training on an unsupervised scenario, and if you are training on a reinforcement scenario, then three things are required: observation, reward, and your action. So observation is, for example, eating chocolate, right? Whatever the taste you feel, that's the observation. Action is go and eat chocolate again. Reward is your you get scolded from your parents, okay, or your let's say guardian, okay. So that three things are involved. So let's just mark them here. In supervised case, we have this x to y pairs, okay. Now in unsupervised case, we are doing x to x mapping, and in reinforcement learning case, what we are doing, we are taking from state is also represented as x sometimes, okay. So we can represent it as state underscore x, sorry, underscore x. So you know that, okay, it's similar to feature. Sorry. Okay. So Sx means state. So that's the general terminology they use, okay, for the literature. And what you do, you take an action at a time t, okay. So yeah, also because states are also time dependent, you can have states represented as like this. So Sxt, so state represented as x at time t, you take an action at, right, and you get a reward rt. So that's the three type of learning task this entire domain has, okay. So now any doubt up to this point? You can, so just for your understanding, you can put the examples too. So it's three people. Can anybody volunteer and give me three examples based on your understanding till now? What is supervised? Just give something that you see in your daily life. Yeah, go ahead, guys. Just unmute and speak. So anybody want to give an example of a supervised learning scenario in daily, like in day-to-day life?
Whether someone passed the exam or not?
Yeah. Uh, can you repeat what you told?
Whether someone has passed the exam or not?
Uh, passed the exam or not? Yeah. So it can be based on someone's class test results. Class test, right? This is X. This is X. Pass the end same. This is Y.
So for supervised learning, every day will rice, one for one glass of rice, one glass of water. So I'll train. So as I increase the glass of water, so I can predict for 4 glass, later I may require 4 glass.
Exactly. Let's say cooking scenario. So how many how many glasses of water required to cook rice? Cook how much rice? So in that, sorry, water. So this water could be how many glasses of water is required, right? So this is Y. This is what I'm trying to predict, right? And how much rice I have, that is X. Yeah. So two examples, good. This is fine. Now unsupervised.
Sir, clustering my pet animals between dogs and cats, depending
Yeah.
on what type of food they eat.
So not dogs and cats. For dogs and cats, you have the labels, right? So you already know the clusters, right? So a good
Yes, sir.
kind
Only
of,
animals.
yeah. So
Types of customers in shop, whether they are a student, teacher, or what profession they are from.
Yeah, that can be one clustering, right? So based on someone's, let's say, buying habits. So let's say in a shop, what someone buys, based on that, I can group them, whether they, let's say they are students, they are bachelors, or they live with the family, right? So let's say if somebody is going to the supermarket and buying, let's say raw vegetables like or rice or like raw vegetables that are in the market, and when some and in contrast someone is going there and buying packaged food, right? Based on that I can group them, whether they are so that association comes later, right? When I go and verify whether my associations are correct, but I can group them that okay, based on someone's buying habit, I can group them. Now,
Sir, explain unsupervised X dash X once again.
yeah, can you just repeat once? I didn't, or your voice is not clear actually.
Sir, unsupervised X arrow X, how we can able to X from X to get output. Once again explain.
I still didn't hear you. Anyway, just try writing it in the chat. I guess there is too much noise in your microphone. Okay. So I cannot decode what you are saying. So anyway, so you get the whole point, right? What is uh, and let's say after I group them, I can go and ask some of them to confirm whether I have grouped them correctly or not, right? So yeah, so a kind of experimental unsupervised learning case is when let's say you are trying to identify a particular, let's say particular medicine, whether it works on or how it works on different group of people, right? So in Go, you give that medicine to different, let's say different set of people, and those
Sir,
people volunteer in your
sir,
study.
X arrow X unsupervised.
Yeah. So when you are
X,
trying to identify, yeah, exactly. When you are trying to identify relations between X to X.
yes, sir.
So it's like whether two person are similar, whether two person are different. That's it. Right. So for example, another example could be how a particular medicine work on a group of people, right? So there can be different type of people, different age groups. Somebody can be, let's say, allergic to some medicine. Somebody can be, let's say, not allergic to some medicine. Based on their effects, we can group. Based on the side effects of the medicine, we can group people, right? And what will be my understanding that okay, this medicine, if given, cause this type of side effects in this set of groups, in this group of people. So whenever, let's say, some participant have, let's say, pre-diabetic patients, so those kind of gives an allergic reaction to the medicine. Okay, so these type of findings I can have by grouping people. Okay, based on their like reactions to a particular medicine. Okay. Okay, so for example, not medicine, let's say vaccine, for
Thank you,
example.
sir. Thank you, sir, for
Vaccine.
response.
Vaccine. Now, what is reinforcement? This is very much easy. You get
You told, sir, vaccine that works for group of people. Reward component will be allergic or non-allergic. That is reinforcement.
yeah, exactly. So whether that vaccine works or not, right? Whether I should keep testing that vaccine or like stop producing it further, right? Yeah, so that can be one good like kind of extension to this unsupervised task to reinforcement. That okay, what the producers,
Learning
yeah,
a new task. Learning a new task.
learning a
New tasks. Sir.
yeah, reinforcement learning is learning to cycle, let's say. Learning to ride. a cycle or bike. Okay. Okay. So now all these three categories are very clear to you. Now we will focus on reinforcement learning. I guess it is till your week 3 or something. Let me check.
Actually, learning a bike or a cycle will also fall under unsupervised, right, sir?
No, so there that interaction is there, right? So anyway, so you can always have this state association. So reinforcement and supervised, unsupervised, they're actually very closely linked. Okay, you can always have an unsupervised problem within a reinforcement problem. Okay, because what you are trying to do actually, in which state you are clustering states, you are grouping states actually, ST. So in which state I should do what, right? This is what you are learning through reinforcement. So in any reinforcement problem, there is always a unsupervised learning part. Okay, but the reinforcement, what is extra? You learn associations. So even after grouping states, you are associating that, okay, whenever I am seeing this group of state, I will take a left turn, I will take right turn, like this. So those associations or state to action associations are learned by reinforcement. So riding a bicycle inherently means it's a reinforcement task, but internally what you are doing, you are basically clustering that, okay, whenever my bike is going straight, I should not suddenly move left, right? So those going straight, this whole state space are clustered together, are grouped together. Okay, so that whenever you are within this group of states, you will not suddenly move left or suddenly move right. If you suddenly move right, you fall down from the cycle or bike, and then you get a -1 reward, right? So that those suddenly braking or suddenly taking left right, these things, these probabilities are reduced, and keeping your handle straight, that probability is increased. Okay, so just to put it in a pictorial form, let's say you are okay, you are riding a bike. So let me just try to draw it. Okay, now you are going straight, right? So that means the entire observations you are having, that is multiple state, st plus 1, st plus 2, let's say for up to 5 minutes, right? St plus 100 up to. These all states are grouped into straight, going straight, right? And what is the action associated with it? So there can be multiple actions associated with it. You can go straight, you can turn left, you can turn right, you can suddenly brake. These are the actions possible. Now, what are the probability distribution for actions? Going straight has the highest probability, and other actions have like minimal probability, very less probability. So you will mostly take, you will going straight action. So this association based on this group of states, my action is going straight. This association is learned by reinforcement, and the unsupervised task is to group these states. Okay, there can be another set of states, that means you are taking a turn. Okay, there can be another set of states. So taking a turn, that means you are more probable to take left or right. So going straight is not a option. You are more probable to take left or right, right? And then sudden brake is not an option. So in that case, the association would look like this. So you get the point, right? In your mind, you are creating this state clusters of what you are seeing and associated action distribution, right? So this action distribution, it is actually created by reward function. So that's reinforcement, and this unsupervised clustering, whatever you are doing in your head, that is unsupervised. So we can say that every reinforcement task, or basically every unsupervised learning task, is comes within the reinforcement learning task. Okay. Okay, just conclude this part. Okay, so landing a bike, it is clear now. So any doubt till here? We'll go for regression then.
Excuse me, sir.
Yeah, go ahead.
Sir, is reinforcement learning is based on feedback, like the machine learns from the feedback whether the response is good or bad?
Exactly, exactly. So reinforcement learning, the whole thing is you see something, you act something, you get a feedback or reward. Okay, that
Okay,
entire
sir.
loop.
Thank you.
So if I can show you reinforcement learning, right? Yeah, see this. So this is the state, this is the environment. Let's say a mouse is trapped in a maze. Okay. Now it is trying to find this cheesecake. Okay. So reward is whether it is getting closer or getting farther. Okay. Now what the mouse sees a like subset of the entire world, right? It sees until it is visible. So that is the state it is observing. Based on that state, it is taking some action. So this is the observation that the mouse has based on the nearby walls, right? Based on that, it takes some action. It take, let's say it go to left or go to right or go straight. And then based on that, it smells the cheesecake, whether it is going, yeah, whether the scent is more, so the reward will be +1. Whether the scent is less, the reward will be -1. Okay, so what it is learning? It is learning to find out the cheesecake. Okay, so this is a kind of good example of reinforcement learning. Same as your bike driving, right? So whenever you are riding a bike, first you what is the state? Whenever, let's say, you are trying to pedal, right? That thing you're pedaling, so that whole sensory inputs that you're getting, your visual input, your audio, your acoustic input, your sensory inputs, everything you are getting, that is the state. And whether you fell down or not, right? Action is what, with how to pedal, which like whether to turn left or right. Okay, and what is the reward? Whether you fell down or you keep going. Okay. Okay, so now let's discuss. So at this point, I guess it is pretty clear what these three type of learning tasks mean, right? And this is true for both machine learning literature as well as deep learning literature. Only thing is that function f, that function or black box changes. So for machine learning, there is this set of algorithms that comes under this machine learning umbrella. And whenever we move from this statistical or this efficient algorithms to a kind of loosely formulated algorithm called neural networks. Okay, so why I'm saying like so it's like you are not bounding or you are not defining this function. Okay, defining the black box, you are giving it a kind of capacity to learn. It can learn any type of function. It's not bounded by your definition, right? So what machine learning is different from deep learning, how it is different from deep learning? So in machine learning, you are actually uh, like defining what the function look like. Okay, so for example, linear regression, in that case, you are defining that, okay, my function looks like a linear function. Okay, so your function can only represent a linear model, a linear function, or my function looks like an exponential model, right? So your function would only represent an exponential function, arbitrary exponential function, but exponential. You cannot represent a, let's say, a logarithmic function with that. Okay. So then in that case, it is called a machine learning problem. Okay. So whenever you are defining the domain and subdomain of the algorithm. Okay. Now, what is machine learning? In machine learning, you are not defining the function. You are defining the capacity to learn. Okay, so we'll later on clarify what is the capacity. So you are defining a function that has some finite capacity to learn any type of function. So if you give it more capacity, it will learn more complex functions. Okay. So those are called deep learning models. So for example, these neural networks, right? So neural networks can be of any type, like multiple types. So there are this linear, like sorry, this like dense layers, right, or linear layers. there are these nonlinear activations between these layers, there are convolutional layers, other layers too. So those things will come later on in the weeks. So anyway, but there can be multiple type of deep learning models that represents a capacity to learn, not specifically a function. But for machine learning algorithms, there is a fixed prototype on which the model can learn. For example, linear regression. So we'll discuss what is regression classification later on. So for linear regression, your function can only represent a straight line. It cannot represent a curve. Okay. So difference between machine learning and deep learning, what we understand. So ML has a definition of the black box model and restricts what it can learn. For example, a linear, okay, and deep learning does not restrict the structure of the function of the model, rather limits its capacity to learn complex functions. So what do I mean by limits its capacity to learn complex functions? For example, go ahead if you are asking something. Hello. Okay, so moving on. So what is mean by capacity to learn a complex function? So for example, I know that if I can learn logarithm, I can learn exponential and linear. Okay. So if my model has capacity to learn a logarithmic function, it is obvious that it can learn an exponential function, a linear function, okay, or a quadratic function. Okay. Now if my model is able to learn a quadratic function, it is not able to learn it may not able to learn an exponential function. So that is the capacity. Okay. So we can kind of rank these different structure of functions based on their complexity. For example, the lowest complexity is linear, next is quadratic, next let's say exponential, logarithmic, like this. So if my model has capacity to learn a logarithmic, it can learn any of them. Okay. But for machine learning, you cannot define, like you have these three nudges to choose. So you can only define logarithmic function. It can only learn logarithmic. You cannot learn linear with the logarithmic machine learning model. Okay. But it will be very hard to learn. Same, but if you define a linear model, you cannot learn so anyway you cannot learn a quadratic model. But let's say if you define a quadratic model, you cannot learn a linear model in machine learning. But for deep learning, it kind of becomes a spectrum. So if you go upper, you can inherently learn the lower capacity functions, the lower complexity functions basically. Okay, so you get the point, right? Now let's discuss what is classification and regression. So the major theoretical concept of machine learning, what is the difference between machine learning and deep learning and its subtasks, for example, supervised, unsupervised reinforcement. This was very necessary. Now two type of, so now classification and regression, these are actually sub problems of supervision. Okay, so you obviously need a supervision.
Sir, I can say about classification and regression a little bit.
Go ahead.
Sir, basically classification is a category is something like a season, when rainy season, winter season, summer season, spring season, and regression is about something number, which is temperature, like
Exactly.
a degree Celsius and humidity.
Exactly. So yeah, so the basic concept is very much easy. So whenever you have categories to learn, for example, you have some x, for example, just forget about x. So x is something that gives me a relation to y. Okay. So x can be anything. but my y defines the task. So if the y has categories, so my set of targets or set of labels, it's countable. Okay, countables means it has categories, right? So countable means let's say it only has 5 possible values. The label has only 5 possible values. That means that's the classification task. Okay, I can classify between those 5 values, 1 to 5. But if it is not countable, okay, if there can be this infinite number of values possible in the label class, okay, so that basically means L belongs to real number set R. Okay, that means what? It can range from any value, minus infinity to plus infinity. Okay, or it can range from a fixed interval as well. For example, it can range from -10 to +10, but can have all possible values between -10 to +10. There are infinite possible values between -10 to +10, right? So whenever my label set is countable, so countable, it's a classification. And whenever my label set is not countable, it's a regression. Okay, now example, classification example, cat and dog, right? So I have some pictures with me. Let's say these are the pictures. Okay, so I can differentiate between them with something like a straight line, for example, right? So all the pictures that now how I am placing pictures in a 2D space, it is complicated, but later on you'll understand that we can have this type of representation of pictures, that we can place pictures in a 2D space. Okay, so there are this PCA, LDA, all those things we can do dimension to reduce the dimensionality of the image. For example, let's say you have your 1080p image, right? So all values of those pixels are one dimension. Okay, so there are how many pixels and how many values basically? So 1920 cross 1080 cross 3 RGB 3 channels. So these are the number of dimensions you have in an image, right? So how I am supposed to place it in 2D? It is not possible, right? So what we do, we basically reduce the dimension in 2D by some method. It's PCA and LDA. We'll discuss them in the next week. Okay, or any other method. Deep learning methods are also there. And now after I reduce the dimensionality, I can just use a straight line. If it is right side of the straight line, I classify them as dog. If I am, let's say, left side of the right side, classify as dog, left side classify as cat. Okay, so this is what classification looks like. Now if I have multiple classes, if I have 3 classes, how does it look? There can be another class too. So what could be the color? Let's say black, right? So there can be, let's say, duck. Okay, so these are duck. So cat, dog, and duck. Now my decision boundary has to be multiple linear lines. So look, for example, let's just connect them one. So one linear line, two linear line. So now what I have is now. So if it is right of the top of the line 2, then it is a dog. Okay, let's just extend it further. If it is left of line 1 and top of line 2, right, it is a cat. If it is bottom of line 2, only bottom of line 2, I don't, because there is no class here. Okay, I can only rely on line 2's property, that okay, if it is bottom of line 2, it is a duck. Okay, so this is what classification means. Now what is regression? So So regression is, let's go for 2D. So 2D is good to understand, right? Let's say this is area of house, and this is price or sale price. So there can be this type of relationship, right? Yeah, there can be this type of relationship. That okay, up till some area there is a like highest value, then it saturates. So even if the property is getting bigger and bigger, it will, let's say something like 100 billion, right? So that's too much money, but anyway, you get the point that okay, there is a maximum area that is possible. Beyond that, everything kind of it's too much, so it flats down. Okay, so this is what regression means. Now I have let's say, wait, let me put it in a different way. Okay, so that you understand what do we need it actually. So now I cannot go and so see this area of house, it's a real number, right? It is a real set, and sale price is also real. So there is no possible way that I can go and find all possible points in this X scale and all possible points in the Y scale, right? There is no possible way. So there are like infinite number of combinations possible from area of house and sale price. So what I will do, I will try to go and sample data based on, let's say, some sale site or somewhere, right? I'll go and sample data. Let's say these are the samples I collected. Let's say 20 samples, right? Okay. So this is a sample I collected. So what is regression? Now there will be a consistency. I have structured the material something like it leads to the next topic. So what is it exactly, right? So this classification regression, it leads to the bias and variance topic. Why? Because from from classification perspective, it is not that much obvious, but from regression, it is very much obvious. See, these are the samples I have collected, right? So what are the possible ways I can reach them? I can predict them. So one possibility is I can build a model that predicts, sorry, just connect it completely. I can build a model that connects all of the observations like this, right? I can also build a model that connects the observations like this, right? I can also build a model that connects the observations like this. Okay. So see, these are valid things, right? So let's just make this one a bit competitive like this. Now, which one is the best one? So can anybody want to guess which model is the best, or which curve is the best fit for this set of data points?
Second one.
Which one?
Second one.
Yeah,
Red
so
one.
red one is the
Green.
best fit. Green one, right? So see, there are two different opinions. One is green. Okay, we can just poll it, but that would take too much time. But so for understanding, we can see that there are two opinions: green and red.
Basically, sir, the goal is to minimize the error.
Yeah. So which one is the best one? Green one or the red one? Blue one, I can see it is, nobody will say blue one is the best one, right?
But though we can easily see that the error is minimum in green, but I feel the model which we may be predicting or developing, we may not be able to have different values of dependent variable if we go for this green curve. So, I think the red one is the best one because most of the points are near to this line, and I feel the sum of the squares of all these errors, if it can be minimized, then perhaps this line would be the best one.
Yeah, but yeah, so the logic is that okay, all my data points, their errors should be minimized, right? But see, the green curve is actually touching all the points, right? It's touching almost all the points. So if I see the error, if I see the error value, my error would be less for the green. So error less for the green, more for the red.
Would be least in this case.
But that would lead to problems in the testing time, right?
Exactly.
It would lead to overfitting.
Exactly. So let's say my testing data points are this. So these data points, I just kind of hide it from the model. Okay. So let's say these are my testing points. Let's say there are another testing point here. So these points the model doesn't know about. Whenever I'm trying to test the model, now see the test set is much closer to the red line than the green line. Right? So if I just generalize the observation, the test error of the training TR, the green curve is less, red curve is more. But whenever I am doing testing error, the green curve has higher error and the red curve has lesser error. Okay. So this is the concept of bias and variance. So there are 4 options. I will draw the matrix here with. So you understand, right? So the curve that best fits the data, training data, might not be good for testing. So what we need? We need a generalized model that works best for training as well as testing. So we don't need a model that fits the data too much. That is called overfitting. So if I just like term them, this green curve is known as overfit. Okay, overfit. Overfit. This red curve is just correct or just right. Let's say there can be like other generalized version too, but for now, let's say this is just correct. And the this blue curve, this is underfit. Okay. Now, what is bias and variance in this case? So by bias and variance, looking these two metrics, we'll say how we to compute them. I guess you have already seen from the lectures how to compute them. We'll just discuss them here again. By computing these two parameters, I can say whether my curve is overfitting or underfitting. So let's just, for example, assume that bias and variance, something we can compute, some metric we can compute. Okay. So let's say this is bias and this is variance. So bias and variance, 2 options, high or low. Okay. So there is some threshold below it, it is low variance. Above it, it is high variance. And for sorry, bias and variance, yeah, same for bias, same for variance. Okay. So high, low, low, high. So this is high, low. This is high, high. And we'll see how, like, what this exactly means in terms of curve. Low, low, and low, high. This is the possibility, right? This is the entire possibility space of bias and variance. Now, what is bias and variance? So bias is how much you are off on average from the true value. So mathematically, bias is represented as expectation of prediction minus expectation of true data. Okay. So that means the true data is here, the average prediction. So if you take the average of this entire prediction line, you get an average close to here, right? And if you take the data's average, you will get an average close to here. So this is known as the bias for the blue curve. Okay. Now what is variance? You get the idea of bias, right? What is the average data value of label, and what is the average you are getting if you are following the prediction? That difference is bias. Okay. Now what is variance? Variance is how much it is varying within its own self. So variance means from the average of prediction, how much you are varying in terms of prediction. So y cap square expectation. This one. So here there is no label component. See, so it is actually how much it is varying within itself. So for example, this one, right? It has a high variance, so it is varying a lot, right? But for the blue curve, it is not varying that much. For the red curve, it is also not varying that much, right? So if it's a straight line, the variance is very less. Okay. So from the average prediction, how much varying you are. Okay. So if you are varying too much, that means your variance is high. So for example, the green curve is high variance, and the other two curves they have. So just see from average how much it is varying. So for the red curve, the average is this, and you are varying from, let's say, minus 1 million to plus 1. No, sorry, you are varying from, if I consider this as 0, you are varying from minus 1 million to plus 1 million. Okay. If the price scale is in million. Okay. Similarly for the blue curve, you can compute the variance. Okay. And this is basically all your predictions. You just get the variance. Par of predictions.
So can you once again tell using the graph how we will calculate the variance, sir?
So from the graph, how you calculate the variance? So from the graph, there is no obvious way of representing it in picture. Okay. So the best I can do is do something like this. So pictorially, what variance represents? Let's say you are having this graph, right? Okay. Now variance means this entire area. This area is known as variance. This entire area, this is known as variance. Okay. Now, how to compare whether a graph is less variant? Let's say another graph is there, which is something like this. Okay. Now, what will be the variance for this? Similarly, I can just from 0, I can right? The variance would be the area under this region. Okay. Got it, right?
So can you repeat the definition for bias once again?
Yeah, bias is let's say for bias there will be a true. So what is the true level? You have to have the true level to compute bias. To compute variance, you only need the prediction, right? Because it is how much the curve is varying with its own self. But for bias, you need a true data based on the, so from the true data, how much it is deviating. So what is the representation possibly is, let's say this is the true data, and let's say this is the predicted data, right? So what is the average between this difference? The area between, so this is true data, okay, and this is predicted data. So the bias is the area between this.
Then for straight line, the variance is 0, sir.
Yeah, for straight line, the variance would be 0. Okay. So not exactly 0. So by definition, you can see it is actually average. So it's just way to represent it. Okay. So it is actually average prediction minus. So if you plot the distribution of prediction, if this is the distribution of prediction, right? So you have the expectation of y prime here, and you take all like square of average distances here. This is the variance, general variance formula, sigma. Okay, so by like if I want to represent it pictorially, the variance will be more when the curve is more spreading, and the variance would be less if the curve is not that much spread. Okay.
Please explain the equation. Sir.
Yeah, go ahead.
You please explain the equation of this variance, sir. Exponential of y hat minus e of y hat, the whole task.
Not exponential. It is expectation. Expectation means average. So the equation is y cap. You have the true prediction minus the average prediction. So it's actually variance of y cap. That's it. Okay. So you have, let's say, prediction of multiple y caps. You just take np dot var of y. That's the variance.
Why do we square it, sir?
Square is variance is squared distance from the mean, right? Is standard variance equation. So if I want to, let's say, for example, just to construct, if I want to calculate variance of any parameter z, right? The equation is what? E z minus expectation of z square, and then took the expectation of that. This is the general variance formula, right? So you're just putting y cap instead of z.
Yes, sir.
Got it? Hello?
Hello.
Yeah.
Hello.
Is there any confusion on this? So it's actually computing variance on the prediction. That's it. Statistical variance. Yeah.
Hello, sir.
Yeah, go ahead.
Sir, can you take any real life example for calculating this bias and variance?
Yeah. Okay. Let me.
Sir, you had written that matrix kind like high, low,
Yeah.
low, high.
Yeah. Well. Okay. 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 So for now, let's just go and conclude that matrix part. Then we'll go for a real life example of how to compute this bias and variance from code, right? Okay.
Sure,
So it
sir.
will be more clear. Okay.
Sure.
So you now know what is bias and what is variance pictorially, right? So for computing bias, you have to have the true data, and what you do, you get the difference, average difference between true data and your predicted data, and variance is how much you are varying from your own prediction, okay, over time. That's what variance is. So what is the best or the sweet spot of this? So if my variance is low, that means what? I can generalize to the test set more. Okay. So so that I don't vary too much. So see this overfit graph, it vary too much, right? So that's why it doesn't perform well in terms of testing. But my red curve, it doesn't vary too much. So it is more generalized for testing. So this variance, what is good and what is bad? If it is high variance and low variance, high variance is not good. Low variance is always good. What does it mean? High variance means the model is overfit. Okay. See, these are the associations that we learned by doing experiments. So see, this high variance, low variance, this is kind of, so this is the clusters or the groups of observations you can have. Now, whether it is good or bad, that is based on the entire experimentation that has been conducted in this literature. Okay. So high variance is not good. What does it mean? It means overfit. Okay, and you can see from the graph, the green curve is varying too much. So it's touching all the points, but whenever I am trying to predict the test set, it is not performing good, right? So it is overfitting the data, overfitting the training data. Now, what is low variance? Low variance means it's generalized. Generalized means it is good for testing. Okay. Now, same for bias. What are the two options? High and low. Okay. So high bias means what? You are more far away from the true data. That's what bias means, right? Y minus So expectation of y prediction minus expectation of true y. That is what bias is. So that means what you are by average you are more far from the true data. So that means higher bias means it's a bad thing. And what does it mean? It means underfit. Underfit. Okay. So low bias means what? That means your prediction average is close to the true average. So this is good. So that means it is generalized. Okay. So what are the good combinations here for this matrix? What we want in our study? We want generalized for both cases. So what is generalized combination? Low bias, low variance. So the best model is this low bias, low variance model. This is the best model. Now next is, so this is the best model.
So,
Yeah, go.
doesn't this model depend on the data set that is provided, whether it's small or large?
No, this small and large means what you are saying.
Sir,
Can you
in regards of the complexity of the model, sir.
So see the complexity. So for example, forget about complexity. We are saying that my model can be of any complexity, but I can only judge the model complexity. So see, this complexity term is not quantized. We cannot measure the complexity by some metric. Okay. So what we do, we estimate complexity or basically understand the complexity of the model based on the bias and variance term. So if my bias is low and my variance is low, that means the model has the perfect complexity for the data. Okay. So my bias is low. So my average prediction is close to the average true value and my model is not varying too much. So it is good for prediction. That means it has the perfect, let's go change the color. It has the perfect capacity. Okay. Now what happens if I go for a high capacity model? That means my bias would be low, my variance will be very high. So it will basically touch all the points, right? Exactly this thing. It will touch all the points. So my bias will be low, my variance will be very high. So low and high, this one. Bias will be low, variance will be high. This is the worst model. Worst model for testing. And not exactly worst. We can do worse. Let's just rank them one by one. Okay. So basically, just use the same color as the graph. So my red model is this one, low bias, low variance. Okay. My green model is this one, low bias, high variance. Now high bias, low variance. What is this model? The blue one. See, it is not varying too much, but it has a big difference from the actual data. So that means my bias is more, but my variance is very not much. Okay. So this part is the blue model. Now what is high bias, high variance? Can anyone suggest a graph on this graph? What will be a high bias, high variance graph for this data? Other color. I can go with purple. Guys, do you want to try or I should say?
They far away from the points. That is high bias. And
High bias,
variance
let's say I
also
start from here and
far from the points.
okay, and then I am varying too much. So that means
Too much.
Vertical line.
Variance.
exactly. So this is what high variance, high bias means. So what is the worst? Worst. So this is the worst. Okay, worst, and this is the best. Got the entire bias variance concept, right? Okay. Now see, we explained it from a regression point of view, right? What is a similar observation from a classification point of view? So from classification point of view, there is a really wait, let me, yeah. So for classification, let's have two axes. Okay, so what can be a classification problem for this? Okay, class test 1 marks, class test 2's marks. Okay, based on that, I want to classify whether a student will pass or fail. Okay, so pass means green. Oh, sorry. No. Pass means green and fail means red cross. So based on these marks, what the entire class obtains, I want to classify, right? So let's just mark all the possible points with these two markers. So class test low, both are low, then they will fail obviously. Right? And let's say there is some person who scored less in class test 1 but scored very good in class test 2. Let's remove that, and they passed. Okay, and there are some very intelligent people who didn't score well in class test 1 and 2. I should not say intelligent because you should always perform well in your class test. So for example, there are some outlier peoples who, even though they didn't score well in the class test, they passed the end sem. Okay, and there are these are the outliers. So they like failed miserably on class test 2 but scored relatively well on class test 1, even though they have passed the end sem. Okay, so let's say this is my entire data. So this is what a classification data look like. Okay, so you have these points, class test 1, class test 2, and based on what the person whether the person have passed the end sem or failed the end sem, you have the these markers. Okay, this is a classification task. And now you know what, like by picture, how we can differentiate a classification from a regression. Right? Now, sorry. Now same, we will go for this high bias, high variance, sorry, high bias, variance, and then we have high, low, high, low. Sorry. So high bias, high bias, high bias, high variance, high bias, low variance, low bias, high variance, low bias. Oh, sorry.
Low, high, sir.
Yeah, low, high. The entire matrix is a bit. So high bias, low variance, high bias, high variance, low bias, low variance, low bias, high variance, right? Now we'll plot all these three type of graphs on this. So what is a best model for this, which has low bias as well as low variance, which separates the two classes with the simplest model, right? That's the low bias, low variance. So let's go with the green curve. So okay, let's go with the green curve. Okay, so green curve, low bias, low variance. A best example, sorry, a best example is this. Okay, low bias, low variance. See, the curve is not varying too much. Okay, on its own, it's varying a bit, but it's not too much within that threshold. So high, low, that's it. There is a threshold there, right? So it comes below the threshold, as well as it's not too much far away from the decision boundary, from the visible decision boundary you have, right? So whenever a new, let's say, prediction I need this person or this person, I can predict it based on the decision boundary. Okay, that the green curves gives me. So what the curve give me, if the class test 1 and class test 2 marks are like beyond this boundary, it is pass. If it is left side of this boundary, it is fail. Okay, so this is a low bias, low variance case. Now, what is a high bias, low variance case? It's very obvious. See, if I red curve, high bias, low variance. This is a high bias, low variance case. Okay, high bias, low variance case, fine. Now, what is a high bias, high variance case? And we are choosing extremes because it is better. It is very much easier for you to understand. Okay, so there are sometimes cases where this curve should not be like far away from the decision boundary. It can be also closer here. Okay, it can be here. This is also a high bias, low variance case. But anyway, we are going to choose extreme examples so that it's more understandable from your perspective. Okay. Okay, now let's go for high bias, high variance case. What is the high bias, high variance? This is a high bias, high variance. See, it is unable to classify any data, right? Now, what is the low bias, high variance case? It is important.
Towards red side, sir.
Yeah. Low bias, high variance case would be this one. This is similar to what was the low bias, high variance case for the regression one. Let me. Green one, right? The green one. Here you see it's touching all the points, right? So for this case, my low bias, high variance case would look like this. Get it? Right? Now, here the person is actually, let's say, failing, right? But my low bias, high variance curve is actually predicting, okay, it is passing because it is right side of the curve. But actually it is failing. See this test example. So it's actually misclassifying. You get the idea, right? All the three type of all the four type of high variance, low bias cases.
So can you explain for the green one once again?
The green one, right? The green one is low bias, low variance. So it is also going closer to the actual decision boundary, as well as it is not varying too much. See, this black curve is varying too much. It is going closer to the decision boundary, but it is varying too much. Right? But the green curve, it is not that much varying. Okay, but it is going closer to the, so it's low bias, low variance. Variance means what? It's not varying very much with respect to itself. So you see this curve is, so the green curve looks like this, right? It's not that much varying.
Yes, sir.
Okay. Okay. So now,
Sir, how to deal with the outlier cases in the best case? Like in the green one, we had some outliers also, na?
yeah. So in green one, there are outliers. So not outliers, we can say them as misclassified examples, right? So in those cases, we considered that the model cannot have perfect test training accuracy, right? If the model has perfect training accuracy, then it is overfitting. So that means it's a low bias, high variance case. This happens when the training accuracy is or training error is very less, right? But you are expecting more error in testing. But for low bias, low variance case, there can be examples when the training, let's say in training example, it sometimes misclassifies some examples. So the training error or training accuracy is not perfect. But in testing, you will have less error than the model which is having very much good accuracy in training. Got it? So for example, this, right? The green curve can predict that, okay, this testing example is cross and this testing example is pass. But for the black curve, it is not, it is like both are pass. So for testing, the black curve is not performing well.
Okay, sir.
Got it? Got it? Okay. Okay.
Hello.
So yeah, go ahead.
Sir, I have one question.
Yeah.
In case of linear regression, we do y hat is equal to beta 0 plus beta 1 x1. So why do you need the beta zero? Why we are considering zero? We
Yeah,
can
beta
direct
zero.
y hat is equal to beta one x1 and then predict the beta one value.
Yeah. So see.
Hmm.
So for a linear equation, there are actually two things that matters. One is this slope, right? This slope. This slope is represented as beta one. And then another thing. So see, if I only have beta one, I can only represent equations that are passing from the origin, right? All the equations, possible equations that are passing from the origin. See, I can represent all of them with only beta one x, right? But what
Yes.
if I want to represent a curve that is like this? I cannot represent it, right?
Okay.
Yeah, so this is the beta zero, this bias part,
Okay.
beta zero. So what you are doing, you are actually, so the corresponding beta one equation is this. You are doing plus beta zero to shift it upwards, so that you can now have all possible type of curves within this 2D space. Get it? Without the beta zero, you are only limited to equations that are passing through the origin. But with beta zero, you can represent any curve within that 2D space.
So we always need the beta zero in case of linear regression.
Yeah, exactly. So y equal to mx plus c, y equal to mx plus c is a linear equation, right? This is the standard linear equation. So this m is slope or represented as beta 1. The c is the intercept of y. It is represented as beta 0 in machine learning literature. So for machine learning literature, the equation looks like beta 1 x plus beta 0. Okay, so see guys, we are already out of time, but my goal was to also do some practice of linear regression and generalize it further. But anyway, so you can move them to the next week. And see, I will also share you the
Sir,
previous
I
runs.
have a one doubt there,
Yeah, go ahead, go ahead.
sir, which is from the not from this class, sir. That sir, regime of fit score prediction, which regression is followed, linear or logistic or poly?
Resume.
Regime job fit score prediction.
Resume job fit score means whether you are fit for a job from your resume.
Yes, sir, yes, sir, yes, sir, yes, sir.
Yeah. So yeah.
According to
So
your resume.
so there can be two type of approach for this problem, right? One is a scoring mechanism. So
Yes, sir.
score can be, so based on your resume, what score you get, that can be real number, right? It can vary from 0 to 100, any possible
Yes, sir.
fractions also. So in that
Yes,
case,
sir.
it's a regression. Or if the hiring party has categorized participants, that okay, he's the high potential candidate, say mid potential, low potential candidate, right? Or let's say they classified they group the candidates into 5 bins: bin 1, bin 2, bin 3, bin 4, bin 5. In that case, it's a classification problem. So based on how the hiring party like models the selection process, how they're evaluating it, whether they're evaluating it based on score or whether they're evaluating it based on the
Category.
potential of the candidate. Yeah. And anyway, so at the end of the hiring, it is a classification problem, right? So even though they are trying to predict a regression problem, for example, score, there will be a threshold set. For example, if my score is more than 50, I will get called for interview, I will not. So at the end of it, it's a classification problem, whether you will get interview call or not. But
So,
before
so
it,
this is not a problem of regression,
yeah,
according
before
to you.
no, before it. So see, based on my threshold, it can be converted to a classification, because you see, whenever you are doing an interview schedule, right, what you will see if you are regressing score. If my score is more than the 50, right, average, I can call
Yes, sir.
that participant or call that candidate, or I will not call that candidate if the score is below 50. So my problems set, like problem formulation, can be both regression or classification, but my outcome is always classification, right? Whether I will call for interview or not, right? So for classification also, see, I can have 5 classes. I can have this type of 5 classes for evaluating a candidate, right? Where is my
Okay, sir.
Yeah, I can have 5 classes. Let's say high potential candidate, mid potential, a normal, low, very low. These type of 5 categories, right? I will only call people who are more than normal. So I will only give a call to this or reject this. So at the end of the hiring process, it's a classification task, or I can formulate it as a score. Let's say score varies from 0 to 100, and I can only give call to whichever has more than 50 score or less than 50 score. So if I formulate the problem like this, it's a regression problem. If I formulate the problem like this, it's a classification problem for machine learning. But my like overall objective is to whether keep call for interview or not call, right? So in that case, I have to choose a threshold. Okay, and the entire like end outcome is a classification, whether I will call or reject.
Okay, sir. Sir, we are beginner in machine learning. All of the candidates who are present here, so we can able to make it through regression.
Yeah, or classification, whatever you like. You can directly classify call or reject instead of going with this deeper, let's say hierarchy, this high, medium, normal, low, very low, or this score. You can directly predict call or reject, right? Then it's a classification.
Okay, sir. According to
Yeah,
thank you.
it's like how you set up the experiment. That's it. That's the entire.
How
Yeah.
how the trend of data is data sets. It is
Yeah.
score.
Exactly. So
It
based
is
everything is dependent on your choice. So how you choose the
thank you,
problem
sir.
to formulate.
Thank you for
Okay. Okay. So so we'll stop here. So bias variance. So the part that are remaining is linear regression and what it mean in code, logistic regression, what it mean in code, and how it generalize to when you try to predict multiple values. Okay. Multiple like let's say you are trying to predict a plane, right? Or you are trying to predict a 3D object. So in that case, there are multiple values that has to be predicted. Or let's say you are trying to classify between 10 possible categories, right? Instead of 2. In that case, you are trying to predict 10 possible categories. So those things actually generalize. So today we see only binary classification and one like single value regression, right? It can generalize to a plane or a 3D object or a metafold of 4 dimension, 5 dimension, or in classification, it can go up to let's say 100 class classification like this. So we will see those things in the next class and also discuss this dimensionality reduction. And by the way, so I was planning to like do the question answers for week 1 and week 2, but we are out of time. So what I can do, I can share you the like these things already have the solutions. Okay, so from the previous run, the solutions are already given here. Okay, so I can share you via this drive link. See here.
Sir, can you
This is
share this slide,
yeah,
wall slide with you
everything will be
covering
shared.
this class?
Everything will be shared. I will post this thing in the WhatsApp group.
Okay,
Just
okay,
like
sir.
week 1 resources, I will post it. So you can see the previous year questions folder here. Sorry. Uh, sorry. Back it up. Okay, this previous year questions here. Here there is a doc file. Okay, there I will put up to week 2's assignments from previous run. Okay, and you just go through them over this week. If you find any confusion or any doubt, post it in the WhatsApp group. Okay, and we can just quickly go through them, all the doubts you have in the beginning of the next session. Okay, because these are like MCQs and already the like it's just by I have to just go and read through them. So at this point there are no, and see these type of things we already discussed, right? So which are the functions overfit the training data? Now you know that F2 will overfit the training data, right?
Sir, but that beta for bias, I didn't get, sir. Beta naught and beta 1 you had
Yeah,
explained.
beta 1, beta naught is basically a this machine learning terminology. So if you just go and see this 10th class linear algebra or 12th class 10 or 11th class linear algebra book, this linear equation is represented y equal to mx plus c, right?
X
Where
rate.
n is the slope. Yeah, straight line. Straight line is represented as this equation mx plus c, where m is the slope, c is the y intercept, right? So in that case, this in machine learning literature, this m is represented as beta 1 and c is represented as beta 0. That's it. No more, like nothing else. So the exact equation is written as like this: y equal to beta 1x plus beta 0, where beta 0 is the y-intercept and beta 1 is the slope. And what do I mean by y-intercept? This is the y-intercept. This is this value. This value is beta 0 and the slope, this is beta 1. Okay.
Sir, so in this case of problem, what will they ask, sir?
Yeah, I didn't get the question. Can you just repeat?
So the beta 1x and beta naught, the equation you showed, what type of problems will they ask in that, sir?
So you can just go through these problems. So these are previous runs assignments. You can just go through them. There will be similar type of problems. So just to, for example, they can ask like given some data, compute beta 0, beta 1. Okay, so what you have to do, you have to use that x transpose x inverse x transpose y equation to come up with that beta 0, beta 1 matrix. And if you just go and watch the previous week's slides, so I guess it's already open here. We have actually done that. We have actually used this equation to compute beta 0, beta 1. See? Yeah. So my so the ground truth equation have beta 0 as 0.5 and beta 0 as 2 and beta 1 as 0.5. After I ran this equation, my computed beta 0 and beta 1 is exactly same. So you can be asked to, let's say, for a small toy problem with 2-3 data points, compute the beta 0, beta 1. Okay. But
Yes,
anyway, so
got it.
those are subjected to like whether that is a long question or whether, so there can be essay type questions as well. Okay. So I have read the guidelines. There can be this explanation questions as well. So in those cases, you have to let's say derive
So
something. So
previous year questions for week 2 as well, sir.
yeah. So these are the questions from previous year's week 2. So I will share them and send you the link in WhatsApp. Uh, so all these questions will be shared with you. And the questions are already, you can see the right answers are marked. So accepted answer are these two. For here, accepted answer is F2, F1. So just go through them. I don't think that you will face any problem. But if you face something, just put it in the chat. Right? See here, bias and variance is given by. See what the equations we just saw. Right? See, it's a expected variance of the prediction and it is the expectation of the prediction minus actual data. Okay.
Sir, how to join the WhatsApp group?
You can use the link in chat, right? There is a link in chat. See?
Okay, sir.
Sir, can you repost that link? Yeah, got it.
Got it, right? So just copy and paste it again. Okay, so I will share because group 3's assignment is currently like what you are currently doing, right? So I will share up to group 2 because there can be these overlapped questions between this run and previous run. So if I just share group 3's question, it can happen that you get multiple question common in this year's assignment too. Okay, so it's not ethical, so I'll not do it. I'll share whichever group ended, I'll share that assignment from the previous year. Okay. Okay, guys, so I will share this 2 weeks assignment, week 1 and week 2 with you. You just put all the doubts in the WhatsApp group. We'll address them in the beginning of the next week, or will, if it is very minute or very easy, I can just answer it in the group itself. Okay. But
Okay, sir.
let me stop sharing. I'll stop recording. Okay, guys.